So in this lecture, what we're going to do is we're going to look at and use the periodic table of elements to determine how many protons, how many neutrons, and how many electrons are in an element. Now to do this, we have to define several terms. Okay. The first of them is the atomic number. And what this number is the number of protons in a nucleus. Okay. Remember that the proton is what determines the element type. So if we look at the periodic table here, and we're going to look all the way over on this side, and we see H. That H means helium. Sorry, damn it. Not helium, hydrogen. That H means hydrogen. He is helium, which is number 2. The H means hydrogen. And that has a number 1 right next to it. That is the atomic number. The atomic number. So we see that it is 1. So that means there is 1 proton in hydrogen. Okay, so hydrogen, atomic number, equals 1. Okay. Now we have to say, well, how many neutrons are in the nucleus? Because remember, in the nucleus, we only have 2 subatomic particles. We only have protons and we only have neutrons. So there are 2 ways that we can do this, and they're both related. So in some periodic tables, you have a whole number that is called the mass number. And it's usually it's a whole, and it's not usually, it is a whole number. Okay. And this mass number, if you see it, is the total of protons and neutrons in a nucleus. Okay, so if I have the atomic number and I have the mass number, I can figure out how many neutrons are in the nucleus of an element. And the way you do this is neutrons equals the mass number minus the atomic number. Okay. So let's look at hydrogen, for instance. Okay, hydrogen has an atomic number, we already know, of 1, and it also has a mass number of 1. So for hydrogen, to figure out the number of neutrons, what we have to do is we have to take the mass number, which is 1, minus the atomic number, and that gives us 0. That means in hydrogen, there are no neutrons. Now let's go over to the edge of the periodic table right here, He, helium. Now helium, its atomic number is 2. And its mass number is 4. So the number of neutrons is 4 minus 2, which gives us a total of 2. So helium has 2 neutrons. 2 neutrons. Okay, so let's look at another one, because the rule of 3 is if you can do 3, you can pretty much figure, if you go through 3 examples, you can figure them all out. Now let's look at oxygen. Let's look at oxygen. So oxygen, which is O, okay, it has an atomic number of 8. Okay, and it has a mass number of 16. So the number of neutrons inside of oxygen is 16 minus 8, which is 8. So there are 8 neutrons in oxygen. 8 neutrons in oxygen. Okay? Now, all good, all fine. Now, one thing that we find, actually before I go on that, there is another way that you can find atomic number, and basically it involves rounding, and then you have to apply the formula. Sometimes you aren't given the mass number on a periodic table. Sometimes you are given this thing called atomic mass. Now, atomic mass is the actual weight of an element. Okay, and usually they're decimal, so it's a fraction of a whole. So for example, if we look at our example here, let's look at oxygen. Oxygen's atomic mass is actually 15.99. 15.99. So in order to get the mass number from the atomic mass, all you do is round to the nearest whole number, and that will give you the mass number. So if I have an atomic mass of oxygen, which is 15.99, the nearest whole number is 16. Then you just plug it in to the formula. Mass number minus atomic number will give you the number of neutrons. Okay, so that's it. So those are the two scenarios, to figure out a neutron. Now the problem in nature is that not all atoms of an element have the same number of neutrons. Okay, so like for example, carbon. If you look at carbon itself, the most common form of carbon has 6 protons and it has 6 neutrons. Okay, and then 99% of all carbon is carbon-12. Okay, 6 protons, 6 neutrons. The mass number is 12. Okay, in nature, what we find is that about 1% of the carbon is carbon-13, which means that it has 7 neutrons, or carbon-14, which means that it has 8 neutrons themselves. So when you have an element that has a differing number of neutrons, that is called an isotope. An isotope is an element with different neutron numbers. Okay, so let's use hydrogen as an example. So hydrogen, we know that hydrogen has 1 proton. So we can put here 1, it's got 1 proton, 1 little plus sitting out here. Now, if I have hydrogen, and that is just hydrogen. Okay, and remember, the thing that makes it hydrogen is the fact that it's got 1 proton. 1 proton. Now, if I have hydrogen with 1 proton and 1 neutron, no charge, 0, it is still hydrogen. Okay, but we would call it hydrogen 2. Okay, and the reason is because its mass number is now 2. It's still hydrogen. It is still hydrogen. It still acts like hydrogen. It's still just got 1 proton. It's just a little bit heavier because there's an extra neutron in it. Okay, and then you can also have, let's say we have 1 proton, and let's say we have 2 neutrons. It is still hydrogen. It is still hydrogen because it has 1 proton. However, we would call this hydrogen 3 because its mass number is now 3. Its mass number is now 3. Okay, so that's all an isotope is. It is just an element that have different numbers of protons. So now let's just say, for example, we have oxygen. So we know oxygen, it's got a mass number of 16 and it's got an atomic number of 8. So oxygen has 8 neutrons. Okay, there are some forms of oxygen that have 7 neutrons in it, but is it still oxygen? Yes. It just had that isotope of oxygen just has fewer neutrons. Are there some form of oxygens that have 9 neutrons in it? Yes, of course. It is just an isotope of oxygen. It still acts like oxygen, but an isotope that has more neutrons is a little bit heavier, and an isotope that has less neutrons is a little bit lighter. Otherwise, they're exactly the same. Where that argument falls apart is if the neutron count is too high, or if the neutron count is too low, sometimes it is radioactive. And when you have an isotope that spontaneously decays, where energy is just spontaneously released from the nucleus, that is called a radioisotope. Okay, a radioisotope. It is an isotope where the unstable atomic nucleus will spontaneously release energy or subatomic particles. Okay, or subatomic particles. And that's all a radioisotope is. Now, we can use radioisotope as tracers. Okay, like if you need to see if a thyroid gland is acting a little funky, so you can actually use radioactive iodine as an isotope of iodine, and the thyroid will take it up, and then you can actually measure radioactive iodine inside of the thyroid gland. You can also use radioisotopes for imaging. So like when you take the barium or you do kidney studies using an X-ray, what they do is you drink that, and it's a slightly radiolucent, and you can actually pick that up on an X-ray. And the reason you do that for an X-ray is because X-rays don't really show internal organs that well unless you mark them. And so that's what those things do. And the principle of this is that these radioisotopes are releasing energy. And so when you bombard them with X-rays, they glow a little bit. Okay, and there's a clinical use for radioisotopes. Okay, more important that you just understand the principle of what a radioisotope is. Okay, you have an isotope, and it's structured in such a way, either it's got too many neutrons or it's got too few neutrons, and what it does is it makes the nucleus of the atom a little bit unstable. And when it's a little bit unstable, what it's going to do is it's going to eject some energy, or it's going to eject subatomic particles to bring it to a stable nucleus. Now, if one of those subatomic particles that is ejected is a proton, you're actually going to get a change an element, because remember, it is the proton that determines the element type, and if you kick a proton off of the nucleus, you changed the element. For example, carbon-14, when it decays, when its nucleus, it's a radioisotope, when it decays, it actually kicks off a proton, or it actually kicks off protons, and it becomes a different element. It's not important that you remember what element it turns into. Again, the important thing about that is you just understand the principle. You don't have to go into such detail, just understand what a radioisotope is. Okay, so now we've dealt with the nuclear components. Okay, now we're going to talk about the electrons, and this is where we get a little bit complicated. Okay, so the electrons. The easiest way to determine how many electrons an element has is to realize that the electron count will typically equal the proton count. So let's take hydrogen, for example. Okay, we know the atomic number for hydrogen is 1. That's the atomic number. So that means we have 1 proton. Okay? We have 1 proton. This also means that we have 1 electron. We have 1 electron. So now, where does the electron go in our model? So what we're going to do is we're going to use the Bohr model, where we have our positive charge sitting in the center. That's our proton. And you know the electrons, what they do is they float around the outside. They exist in energy levels called shells. Okay? And there is a rule that we have to follow when we're trying to build our atoms. Okay? And the rule is called the octet rule. The octet rule. Octet. Let me spell that correctly for you. Octet rule. And this rule states that in the first shell, we can only have 2 electrons. In the first shell, we can only have 2 electrons. Because what a shell is, it's an energy level. It is an energy level. The energy level of that shell can only take 2 electrons. So first shell is 2 electrons. Okay? 2 through whatever you want equals 8 electrons. 8 electrons. Okay? And that's where we get the octet rule. It is 8. So all you have to remember is the first shell, 2 electrons. Every other shell after that, 8 electrons. Now, there is a special name for the outermost shell. So if we look at hydrogen right here, this first shell is its outermost shell. The outermost shell of any element or any atom is called the valence shell. And the electrons on that valence shell are called valence electrons. Valence shell and valence electrons. These are important because these are the electrons that will interact with other atoms. Okay? The nucleus themselves will not interact. The nucleuses of atoms do not interact with each other. It is the electrons that do it. Okay? So, octet rule, the first shell can only hold 2 electrons. Okay? Every other shell after that upwards can hold 8. Now, if you've taken chemistry before, you've taken physics before, you will know that the third shell, the fourth shell, the fifth shell can hold a lot more than 8 electrons, and I'm not going to disagree with you on that. But for bonding, the purposes of 8 will fit us. That's all we need to know. Okay, so we're going to look at another one. Let's take a look at helium. Okay, so we know that helium has an atomic number of 2, so it's got 2 protons. Okay, so we know then it's going to have 2 electrons. Electrons itself. So if we build this atom, it's got 2 protons in the center, so we build our shell, we'll put our shell around it, and 2 electrons, 1 here and 1 there. All right? Do we need to put on another shell? No, we have met the requirements of having 2 electrons, and those 2 electrons will fit in the first shell. So we can say this is a full valence shell. Okay, it's a full valence shell. We don't have to do anything else with this. It has been built. Okay, now let's go on and look at a different element. Let's take a look at carbon. So carbon has 6 as an atomic number of 6. Carbon, the symbol is C. It has got an atomic number of 6, which means it has 6 protons. Okay, and this means it has 6 electrons. Okay, instead of drawing 6 little plus signs, I'm going to put plus 6 in the center here. And then around that, I've got to draw my first shell. So the rule is, how many electrons go in the first shell? It is 2. I can put 1 here, and I can put 1 here. Okay, so I've got 2. How many more electrons do I have to account for? The answer is 4. In order to do that, I have to add another shell. Another shell is added. Okay, so now using the octet rule, how many electrons can we actually fit on this? We can fit 8 electrons on this, but how many does carbon have? Carbon now has 4 that it can do. So we have a spot for 4 electrons. 2, 3, 4. We have 4 electrons in our valence shell. So remember, the outermost shell, now this is the valence shell, and there are 4 valence electrons. Okay. How many electrons can I add to this shell? I can add 4 electrons. Can be added. Okay. When we talk about the next lecture, on the next lecture, I talk about this. We'll talk about bonding. This will be a very important concept. Okay. So what about the first shell? Sorry. What about the first shell inside of carbon? Does it matter anymore? Nope, it does not matter because it's full and we have a shell on the outside. The shell on the outside is going to be one that actually interacts. Okay, so now here's what I would suggest you do. Okay, I would suggest you just take a look at a periodic table, and then just go through and just do them. So draw out the atoms and the electron configurations for carbon. Just do carbon again. Carbon, nitrogen, oxygen, sodium, potassium. Potassium. Is that how you spell potassium? I'm just going to say K for potassium because I'm not 100% sure how to spell potassium right now. I'm having a brain cramp. And for K, potassium. Carbon is C. Nitrogen is N. Oxygen is O. Sodium is Na. And potassium is K. So draw those atoms out. Draw those atoms out and fill in the electrons. Okay, so that's going to be the end of this because we're pretty long. We're 22 minutes. So the next lecture, we're going to talk about how the electrons will interact with each other in forming bonds. Okay, and when we do this, there are 2 main types of intermolecular bonds. There's the covalent bond and there's the ionic bond, and then there's the intramolecular bonds called the hydrogen bonds, but we will talk about that at a later time. All right, that's all I have for this one. Thank you very much.